Okay, so good morning everyone. So we'll start our lecture today. So just a quick question, how many of you still don't have access to Blackboard? So everybody has access to Blackboard, right? And how many of you haven't accessed Slack or Piazza, although there's not much activity there? I think we've made some announcements on Slack about office hours and stuff, so I hope everybody got the announcements at least. Who is not there on Slack and Piazza? Okay, everybody seems to be on the communication channels. Cool. So I've posted the handwritten notes from last lecture. It's quite rough, but hopefully that along with the notes will help you read the recommended textbook, which is Elementary Statistical Learning, or you can go through the second textbook, which is also listed in the syllabus. It's called Introduction to Statistical Learning with R. So it's not math heavy, it's more it's going to give you the intuition about different things that we're going to go through in this course. So if you don't want to see the math for the first time, when you go through the first time, then you can refer to the second book, which is on the syllabus page. Am I audible to the people at the back? No. So there's a reason why you're sitting at the back. Okay, good. I have also posted a couple of things. First is the project details. How many of you have not accessed the project details PDF? Not accessed? Okay. So there is a particular timeline for, you have not accessed because you don't have access to Blackboard, or just not have access? You don't have access?
No, I have access.
Okay, so please check the project details today or whenever you can. It is somewhat open-ended, but hopefully you can pick a project which is commensurate with your background and skills. So you don't have to really work with large data sets and do some very fancy stuff. You can work on something interesting that you can show and talk about even after this class. Even after this semester, you can talk to other people about something interesting that you did here. The second thing is I've also posted the first assignment. I guess writing that assignment was not difficult because I was referencing to standard problems in the textbooks, but hopefully you have access to both the textbooks. They are available online. You don't necessarily have to purchase them, but if you want a hard copy, you can. So hopefully the assignment load is not too high, considering many of you are taking many other courses. So, but do get started. You may not be able to do it in the last minute. There's a 2-week timeline for the assignment. It's due on 22nd midnight. Okay. Yeah, it's all individual. If you can always form study groups and learn about the material, but you should write your own write-ups. And if you do collaborate closely, you may want to mention whom you collaborated with. Okay, it gives us more information. So project is also individual. Yeah. So this is probably different from some of the other courses that you're seeing where you do group assignments and group projects. There's a different format we're trying out this time. So hopefully we'll understand what's the right workload. So, okay. Any questions otherwise about project, assignment, or the class in general? Yeah.
Is it mandatory to do everything on R? Can you use any other?
Like for example, what is you can. So you're talking about, the only way we will look at your R code is through the assignments. So you're saying you don't want to do the assignments in R? There are only 4 questions. I think you can probably do it in R. The project, let's talk about it. You can talk to PAs and me individually, and if the project scope requires a better, some other tool is a better fit, maybe we can make that accommodation. Yeah, but in general, we would prefer R just so that you guys know R at least at the minimum. But yeah, other tools are fine if it's related to the project scope. Yeah. Maybe I should switch out. Any other questions? Okay, so let's start today's lecture. So today we're going to really introduce probability and statistics into the mix. Last time we kind of handled a few things, defined some objective which was least squares. I think last time I also wrote down a closed form expression for the least squares best fit model coefficients, like a vector of the coefficients. I had a closed form expression. So today maybe we'll revisit and derive it, so that you're more confident about, it's not something we just accept as a fact, it's something we can easily figure out, okay? Okay, so let's start with the, so I'll also try to show the notes in case there is, the figures, so that, you don't have to keep the notes online all the time. Okay. So, there's a theory in this name of the section, but it's really not a theory as such. So we're gonna introduce a little bit more notation. So what we saw last time was some functions of data, which was input variables and output variables, and their realizations, right? So this time we're gonna actually say we have a joint distribution, which is written as PR for probability, over the input variables and the output variables. So X is our input variable and Y is our output variable, so a joint distribution on them. So now they have become random variables. How many of you vaguely remember what a random variable is? Good. So how many of you don't know what a random variable is? Okay, so random variable is actually a function, but you can think of it as something that you attach to a random experiment. So for example, let's say you're flipping coins, okay? So let's say you're flipping one coin and it can land heads or tails. Let's say it's an unbiased coin. Unbiased just means that the probability of getting a heads, probability of getting a tails is the same, which is 1/2, okay? So let's say if the coin lands head, maybe you will have a variable X, which will be equal to 1, okay? And if coin is heads, and maybe it's 0 otherwise, which is in the tail situation, then X is called a random variable, and in this case it's a discrete random variable because it's just taking a finite number of values, which is 0 and 1, which is 2. For example, if you roll a die, it's going to have 6 discrete values. Okay. Let's say it's 1/2 if it's an unbiased coin. Last time I think we did use the keyword Gaussian or normal distribution. So a random variable, let's say Z. We're gonna use the notation Z. This tilde sign, probability of Z. So for example, if it's a normal distribution, we'll say Z tilde. We're going to use that notation N stands for normal. And typically distributions are parameterized by some other numbers. So for example, in the discrete case, the distribution is parameterized by number 1/2, right, which is telling what is the probability of heads, right? So similarly, the distribution for this random variable, which is going to be a normal distribution, is going to be parameterized by a mean and a variance, okay? So two parameters, mean and variance, determine completely characterize the distribution. Actually, distribution is not the right word. It's the density of this random variable Z. So Z is a one-dimensional random variable. It's continuous, and it's parameterized by a couple of numbers. The density function for this random variable is parameterized by a couple of numbers. So that's what a random variable is. but you should definitely go through 570 or something equivalent to kind of refresh what a random variable is, because we're going to use the notion of a random variable, essentially three things, which is the notion of a random variable, expectation of a random variable, and variance of a random variable. Basically, those are the three things we will definitely need, and if we need something else, we will rederive it or figure out the intuition behind them as we go. Okay, so this is where the statistics part comes in. I mean, before that, there was no notion of statistics. We had a language which was kind of incomplete. So once we bring in a joint distribution between the input variables and the output variables, we can talk about, really given training data, we can talk about what would happen in the future. Okay, because the training data would be some sort of like realizations from this joint distribution, which is the probability of x comma y, and the future data you would also assume that hopefully it is also realized from this joint distribution. Okay, so that's how future data and past data are related through this object, which is the joint distribution. Okay, otherwise you can't really say if you train a linear regression model on some data xi yi's, which are realizations, but if you're some other x's yi's on which you want to use the linear regression model come from somewhere else, they're arbitrary or something like that, then you can't really say anything about how you're going to perform, right? So that's why we're introducing the notion of statistics and statistical modeling here. The second thing, so with this joint distribution, what we want to know is, we still want to know the same thing. We want a function which maps from the input variables to the output variables. Okay, we want something which goes from x to y. Okay, and we will now again need another function, which is going to quantify how well this first function is going to tell us about the output variable. So it's going to take two arguments. I've used first argument as y and the second argument as f of x. So it's going to tell so y is the desired output value. Let's say I'm using capital letters to just represent them as variables. Remember the notation from the first lecture. So capital Y and capital X are just variables. The values that they take are going to be in lowercase. Okay, but let's say y takes a value, let's say I'll use y0, and let's say x takes a value x0, and somehow I figured out some function. I have a candidate function f that I use to predict y0. Okay, so some sort of a difference between these two guys is what is captured by this L function. Okay, so I'll give you an example, which is example 1 in the notes, which is what we've already seen in the least squares setting. So let's say L of y and f of x is just y minus f of x squared. Okay. So this is just saying let's fix that function. Let's assume we have built a classifier or a regression model. Okay, if we have if we have built it, then it's fixed. Somehow we are able to transform the input variables to the output variables. Then you can just quantify how well you're doing by just talking about some sort of a loss. What is the error between what you wanted to what you want. If you had chosen the right function, maybe this difference is going to be low, and hopefully you'll have less loss or less error. And if you hopefully chose a wrong, not hopefully, but if you chose a wrong function, then maybe this loss number is going to be high. Okay. So this is actually, again, it's a scalar function, which just means that it's going to take values, let's say in r plus, which just means that it's going to take a value between 0 to infinity, whatever, basically in this like this. So between 0 to infinity. Okay. So it's just a number that you can assign, or a score that you can assign to your predictive model for any two input variables and output variables. Okay. So if you remember, the last time we had a scoring function, which was actually I would say empirical. Empirical just means it was using training data. So if you remember last time I was using a summation notation, I was saying, okay, let's sum over I is equal to 1 to capital N, which was the number of realizations of our data, training data. And I was saying, okay, let's do yi minus f of xi square. This is the least square subjective, and then we, instead of f of xi, I was just saying it's xi transpose beta, I think. So last time we were doing that, but this time for any function, we're just gonna, so we actually call this something else, but so this time we're gonna use the acronym expected prediction error, or expected square prediction error, okay, for any model. So for any model, so f is what your learner or your task you would output, okay. Whatever you output, let's fix that to be some f, okay. We don't know. Let's say it's some f, which we need to actually optimize for. But let's say we picked up some f. So the expected prediction error is for that, for example, would be just the expectation. Okay, I'm gonna expand what the expectation is, but expectation of y minus f of x squared. Okay, so this expectation is over the probability of x and y. So this is just a definition of a score. So the intuition here is that when I defined the loss function, I was the two arguments to the loss function. Let's say we fixed the model. Let's say some model is fixed. Was the y output variable and the x input variable, right? Now I just said x and y are actually random variables, which means that they can jointly take many different values, right? Because there is a joint distribution. For example, and I don't want to draw a joint distribution, but yeah, because they take many different values, I'm averaging out the performance, the loss value over all the different values that x and y can jointly take. So what is the expectation? So this is just, let's say x and y are actually discrete, okay, for simplicity. Then it's just a sum over all the values x and y, take. So maybe x takes a, let's actually write it. Maybe x takes a value x and y takes a value little y, and then it's the probability that x takes a value x and y takes a value y times that square thing, which is okay, actually not capital Y minus f of x square. Okay, that is what an expectation is. Expectation. So how many of you are seeing expectation for the first time? I mean, in a long time. Okay. So let me quickly take a minute to describe expectation. Okay. So if you remember the heads and tails example, this is just an aside, okay? So x was taking value 1 with probability 1/2, and x was taking value 0 with probability 1/2. Okay. Which means that x is a discrete random variable. I mean, we use RV to represent the random variable, but it doesn't matter. And the expectation of x is typically with respect to its density function or the probability mass function. But so what happens is, for a discrete random variable, I have pretty much enlisted what all values a random variable will take and with what probability it will take. Okay. So with 1/2 probability it will take a value 1, and with 1/2 probability it will take a value 0, right? So those are only two values that the random variable can take. Okay. So expectation of x is nothing but the sum over all values that x can take, the probability of that value that it takes, let's say some little x, times x, the value and x itself. So although it looks like a complicated formula, all I'm saying is, x takes a value 1 with probability 1/2, so this is just times, and it takes a value 0 with probability With what probability? Yeah. So the expectation here is just 1/2. Okay. It's just a number. So what it does is basically it's an averaging, right? It's taking x takes very different values with different probabilities. Let me just average and spit out a number. It kind of kills the randomness in the picture, because once you take an expectation, there is nothing random here. This is just a constant, a number that you spit out. Okay. Similarly, this is same expansion that I did here, except we don't have a single random variable, but we have two guys, which is y and x, which are both it's a joint distribution now. There are two random variables. So actually, how many of you are not able to extrapolate from one random variable to two random variables? It's not a difficult thing. Let's say there were two random variables. Let me call it z1 and z2. Okay. For simplicity, let's say z1 is also a coin toss, and z2 is also related to a coin toss. Then z1 and z2 can take z1 and z2 can take what's the right way to do this? Z1 and Z2, let's say, we know that if it's two coin tosses where Z1 is following the first, is related to the first coin toss, and Z2 is related to the second coin toss, then Z1 can take a value 1 or 0, and Z2 can also take a value 1 or 0. But when Z1 takes a value 1, Z2 can also take a value 0, right? And when Z1 takes a value 0, this can take a value 1, right? And let's say they are unbiased coins, in the sense, they are nice coins. So you flip the coin, then maybe it's Z1 doesn't affect Z2, so they're what I call independent. So it's just the probability of Z1 and Z2 would be just the product of their probabilities, which is 1/2 times 1/2, and that's true for every case. Okay. So if you see, it's 1/4 plus 1/4 plus 1/4 plus 1/4 is equal to 1. So typically, these numbers have to add up to 1. That's the rule of probability, that the different outcomes, whatever numbers you ascribe to them, 1/2 and 1/2, they sum to 1. So here the sum is 1. And similarly here, each of the outcome has 1/4 probability, and they sum to 1. Okay.
Professor, since we are summing, are you assuming that those two random variables are uncorrelated?
No, they don't have to be uncorrelated. They can be. So here you can put in arbitrary numbers, right? And so here I said, let's say they were. So you're bringing a word uncorrelated. It's different from independence, but let's not go into that difference. These numbers, I just said, if they were independent coin tosses, then I would fill in these numbers that Z1 takes a value 1 and Z2 takes a value 1 is just 1/2 times 1/2. Okay. But those two coin tosses need not be independent or uncorrelated. Okay. In which case here there will be different numbers, 4 different numbers, but they have to sum up to 1. Okay. They may not be 1/2, 1/2, 1/2, 1/2. They can be some other bunch of numbers which sum to 1. Okay. That's for any general joint distribution. So we are not assuming anything about correlation or independence here. We are not saying anything about them, so which means that we are not assuming anything about them. Okay. If you make an assumption, you will state that. So for the purposes of our definition of expected prediction error, this is what it is. So we have defined a loss function which just takes the two inputs, my prediction and output variable, and just tells me a quality of how far they are, right, in terms of, for example, the least squares objective, or basically the squared objective, square difference between them, and the expectation of that is what is expected prediction error. Okay. Now, interesting. So all we've done is actually the reason why I wrote down this expression on this right side. I don't know if you see this. Yeah, is because this is very closely related to this expected prediction error. Actually, it's as if the least squares, or this is called the residual sum of squares. This objective is just an empirical version of this objective. we'll actually get to that again in a couple of, in a few minutes. But you can see that at least the squared, function representation is pretty much the same. Here I'm using xis, ys, which are my, training data, the data that I have, the realizations. Here I'm not really talking about a specific xi, yi as such. I'm just saying whatever values the random variables take, I'm gonna just sum up everything. Right? That's the only difference. But we're gonna relate them pretty soon. Okay. Yeah.
This is exactly sum of all the errors.
Yeah, I'm gonna define RSS pretty soon, but yeah.
Then EP will be the error in an error.
No, so there is no. So what is the question? So this is the, I would say, let's say this is the RSS for now. Okay, some function. Okay, which is a function of your realizations of your input and output variables and your model f. Here, this is a function of your model f and the joint distribution between the input and output variables. It's not a function of data as of yet. I don't know. So we have not yet related EPE with this yet. Okay. Was it causing confusion or any other questions? Okay. Okay. So actually we're going to do our first non-trivial thing right now, which is actually figure out the best model or best F. Okay. So EP is actually giving a score. Okay. If you look at the way I've written it, I put a bracket and I've put an F there, right? So I've kind of, that EP is actually defined using both the joint distribution and an F, right? Although on the left hand side I've just put an F there, which means that for this whole discussion I'm going to assume that there is a fixed probability joint distribution between x and y, and I'm not going to bother changing it. But now I'm interested in changing F. If I change the F to, let's say, some F, F2, then I'll get a different EP number. Okay, EP is essentially just giving a number, it's a real number, right? So it's going to give different numbers for different Fs. Now I'm going to try to figure out what is the best F, which can best in terms of the lowest EP value that you can get. Okay, and the way we're going to think about it is this nice trick, which is okay. So this is a trick. Let me just write the trick. I've not written it in the notes, but expectation, okay, of so expectation. So sometimes okay, if you see expectation, typically for clarity you want to write what is the expectation being taken over. So for clarity I've written that the expectation is being taken over this particular joint distribution or density. Instead of writing PR there, I can also skip the PR and say xy. Those are the random variables. Okay, it's the same thing. The trick is, if you have an expectation of a joint distribution, expectation of xy of some function of x and y. Okay, doesn't matter what function it is. You can just write it as the expectation over x of expectation over y given x. I'm going to say what y given x is in right now, of g of x comma y. Same thing, whatever is inside, given x. Okay, so this seems like a lot of shorthand notation where a lot of things are being assumed. So what's happening here? So let's actually write down the expression. So expectation of xy of any function, we just wrote it last time, right? It's just sum over, let me actually separate the summations out. So summation over x and summation over y. So whatever values that random variable x takes, whatever values random variable y takes, right? And there is this probability of x takes value x and y takes value y times g of little x and little y, let's say. Actually. Yeah. So this is what this first term is, but we can actually just write this as sum over x p of x is equal to x times sum over y of p of y is equal to y given x is equal to x times g of x comma y. Okay, so what I have done here is what is called, this is also a rule in probability that you might have seen or may not have seen. It's just a probability of two events, in generally events, but we can also talk about random variables. But probability of two. Okay, let me just talk about random variables, not events. So let's say n be a random variables, then probability of a is equal to, let me just explicitly write this. A is equal to a, and b takes a value b. Let's say a and b are two random variables, okay, discrete random variables. It's just you can just write it separately as a takes a value a times probability of b takes a value b given a takes a value a. Okay, this is just a rule in probability. Okay. Some of you must have seen Bayes' rule and things like that. It's all related to this, but it's not needed for us. So this is just it's just saying that the joint probability of two things, taking two different values. Two things here are a taking a value a and b taking a value b, is the same as the probability that a takes a value a and b takes a value b given a takes a value a. Okay. So here actually you can actually eyeball something called independence. So if b takes a value b irrespective of what value a takes, then the second term here is just the probability of b equal to b, which means that a and b are independent. Okay. But for us, we just kind of know that this is true, and therefore I've been able to go from this step to this step. So I kind of changed this expression here, the joint distribution, into one term and a conditional term, and this is what is this guy here. Okay. A shorthand notation, but. So why do we need? So for us, I guess we just need this trick to talk about what is the best f. Okay, that's what we want. That's what we want to accomplish, right? To get an idea of what is this best f for EPE objective. So for that, we just need to use this as a rule. How many of you have completely lost what I'm saying here? Yeah, so here let's take this z1 and z2 as the two random variables. Okay. So all I'm saying is probability of, let's say we want to find the probability of z1 is equal to 1 and probability of z2 is equal to 2. Okay. Let's say it's also 1. So z1 and z2 are these binary. They're called Bernoulli random variables, but it doesn't matter. It's just some random variables, okay, which take two values. So the rule that I said that you probably need to remember, or just take it as granted, is just that this is just the probability of z1 is equal to 1 times probability of z2 is equal to 1 given c1 is equal to 1. Okay. You can do it this way, or it is also true that it's equal to probability of z2 is equal to 1 times probability of z1 is equal to 1 given z2 is equal to 1. These are just, they're called, I don't know, what are they called? Sorry, I forgot the technical term here, but yeah, it's just a factorization. This is called, I guess, a factorization of the joint distribution. So all I'm saying is this is something which holds for any joint distribution. So when I say joint distribution, all I'm saying is when you have more than one random variable. Okay, so I have z1 and z2. That's why I call it a joint distribution. If there was only one random variable, I just call it a distribution. Okay, and any joint distribution and for any fixed values that those random variables will take, I can split that joint distribution expression as this. Okay. And it so happens that if z1 and z2 were independent point tosses, okay, then no matter how you split it, let's pick the first case, let's say we split it this way. It so happens that the second term here probability of z2 is equal to 1 has nothing to do with probability of z1 is equal to 1. So the first coin toss being heads has nothing to do with the second coin toss being heads or tails. So it just becomes probability of z1 is equal to 1 times probability of z2 is equal to 1. Okay. In a sense, you drop the. So this is just a notation here with a vertical barrier, which essentially means conditioning. In a sense, remember what happened to the other random variables and tell me what's the probability associated with the random variable on the left. That's what it just means. So in this example with two different coin tosses, as in two independent coin tosses, it's just a product of the probabilities. And this you might have remembered from your if you've taken the stats class. You remember two random variables are independent if the joint distribution factorizes in this way. Factorizes just means it splits into the value that the first random variable takes times the probability of the value that the second random variable takes. Okay, that's just an example of this factorization. Is that clear? Factorization? Because we are talking about things which are not, which are basics, which we can spend time on that for sure, but it will detract from the material that we want to kind of see today. Yeah. We're just asking, so see, z1 and z2 can take two values each, right? So there are four possible values that they can jointly take. 1 and 1, 1 and 0, 0 and 0, 1 and 0, whatever, 0 and 1. Okay, those are four values that they can take. For any, for example, just picked, let's say they took 1 and 1, and I was just asking, in fact, I'm not asking anything here, I'm just showing that the joint distribution can always be decomposed either decomposed as in written as a factor of two things, either this way or that way. Both are fine, it's just a rule, right? You can start with one random variable without the conditioning on another random variable, and you can have the second term which is condition. Okay, so these are just two rules. Okay, and all I've done is just fix the particular realization 1 and 1, and I'm just saying that in the example that I showed earlier, I did mention that they were independent. That's why I got these values as 1/2 times 1/2, because the first one takes value 1 with probability 1/2, the second one takes probability takes value 1 with probability 1/2. Therefore, the probability that z1 takes value 1 and z2 takes value 1 is 1/2 times 1/2. Okay. In this example, I just chose them to be independent, and here I was just saying that if it is independent, then the second term just becomes, you delete the thing on the right side. That's all. But that's not very critical. All I'm saying is for any two random variables, you can always write it this way. And for x and y, I just wrote, I picked x first and then said, okay, let me take y given x. Okay, that's all I've done. And these expectations are just hiding these summations, but you can, if you are getting confused about expectations, you can ignore the expectation and say, okay, let me fix x and y. All I'm doing is, if x takes a value x and y takes a value y, I'm going to split that into x takes some value and y takes a value given x takes a value. That's all. There's nothing, the summations are just irrelevant detail here. And if you actually, think of the summation as another, again come back to expectation line, so then this e of x and e of y given x becomes, these things. Okay. So, nothing complicated going on here, actually. So for us, I guess the trick that we want to kind of remember is that for any function of, let's say, two random variables, x and y, you can always split the expectation of both random variables as expectation of one of the random variables. We just took x because we want to take x. You can always take y, but you will not end up anywhere interesting. So we took x to be the first, unconditioned random variable, and y to be the conditioned random variable. And this is the expression. And if you just remember this as a fact, then we can write, if you see the EPE expression, it is the same, right? Expectation of x and y of something. Okay? This function is just the square of y minus f of x. That's all. So by writing it that way, that EPE of f is the expectation over x and the expectation over y given x, is just a short form for, when I say expectation of y given x, all we mean is the conditional distribution is being used as in the summation. That's all. Okay. Y minus f of x. Okay, it's the same thing. I just replaced the function here. Okay. Okay. So why do I care about this trick? Is to tell you that we want to know the best f, right? F is what is f doing? For every realization of input variable, it's giving me a value for the output variable, right? And here you can see that. Let's say I want to say so f is for every x, it's going to give me a y, right? Some y, which means that let's say I only have 4x values. Okay, x variable can only take 4 values for simplicity. Then for every x, I just need to define what value it takes, right? Maybe it takes some high values, some low values, something. Okay. For every x value, I just need to figure out 4 numbers. The 4 numbers pretty much determine the function, the mapping from input to output, right? So if you write the expression in this way, you will see that if you can have the lowest value for the term before the expectation of x, okay, which means that for every given x, if you can minimize, or not minimize, but for every given x, okay, fix every x, if I can reduce the quantity inside, which is this term, for every x, and then take the expectation, then that is going to be the lowest value as well. Okay. So in other words, in this example, x takes only 4 values. So let's fix the first value. Okay, this is the first value. Let's say. In fact, I did not write the values. Let's say x takes values 1, 2, 3, 4. Doesn't matter. So I'm going to fix x to be 1, and then I'll ask what is the f of x value that will minimize this expression. Okay, the expression inside. Okay, because forget about the expectation outside. I fix an x, and I want to say find me an f of x such that this is minimized. And for the second x value, x is equal to 2, again I'll ask the same question, find me an f of x such that this term is minimized. Okay. So basically all I'm asking is, can you just tell me what value should f of x take for every given x? And it is independent of other x's. So the value that will minimize this internal expression for a given x has nothing to do with the f of x value for another x prime. Okay, so all I'm saying is, if there is an x and an x prime, I want to find f of x here, I want to find f of x prime here. Okay, that's why I'm going to completely define the function. But finding an f of x here has nothing to do with what's happening on this side. That's all. So, which means that this to figure out the best f, all I need to figure out is for every given x, what is the best f. Okay, in a sense, if I know what value I can find for every given x, I can string them together and find this whole function, describe the whole function. Okay, like if I can find the f of x for x is equal to 1, x is equal to 2, x is equal to 3, x is equal to 4 separately, then I can string those values together, like this one, this one, this one, and this one, and that would be my function. Well, I mean, this is just for intuition. And this term inside, so let's look at the term inside. It's the expectation of y, okay, given, let's fix some value x is equal to x of y minus f of x square given x is equal to x. Okay. So I'm just explicitly writing, let's fix a value x, so x doesn't take too many, is not a random variable anymore. Now this expression is minimized at a given value. So if I want to, let's say, minimize over f of x. So if you're uncomfortable with the representation of f of x, you can just replace f of x with some optimization, some variable z. Okay, minimize over z instead of x. All I'm saying is find a z such that this thing is smallest. Okay, and it turns out that z is just the expectation of y given x is equal to x. Okay, so the z which you can plug in some value that you want to assign for f of x, right? F of x that you want to plug in is just this particular expression. Okay, so this is just a constant. Okay, expectation of y given x is equal to x is, since it's an expectation, it's a constant, some number, right? If you want me to expand out that expression, it's just the summation over all y's of values that y takes times the probability of y is equal to y given x is equal to x. That is what that expectation is. Okay. So that is some number. For every given x, I can find this z number. Okay. For every given x, I get a z number. I'm going to say for every x, I can compute this, and that is my f of x, which minimizes the EPE value.
How did you get that?
Good question. I think you can just what is a conditional expectation? Conditional expectation. Okay, I'm forgetting the reasoning. It's actually a simple reason. Let me come back to this maybe in the break or something. Let me try to remember. Then I will try to do it on the fly. Okay, so this will leave it and we'll revisit it. It's not difficult, but yeah.
Can you just go this week now? The graph that is trying to plot.
Here, yeah, this small expression here, yeah.
So basically for one every time I effort is to minimize and be close to the real one.
Yeah.
Right. So are we trying to segment out something that probably in this region the actual graph is minimizing this differentiation over?
No, all I'm saying is, okay, let me redraw the graph so that it's kind of more clear. See, we had this EP expression. We broke it down into this conditional expectation of a conditional expectation. Okay, and let's say x is on this axis, and for simplicity, I said okay, let's take some 4 values. All I'm saying is for every single x, you have this. For every single x, you have this expectation of y minus f of x square given x is equal to x, right? This was the expression inside the thing. So for every single x, you can find this. So finding this, so there is this expression. So you can minimize over f of x, okay, and you can do this for every x. So all I'm saying is, let's say there's x prime. So let's say this is x and this is x prime. Okay, there are 2 values. So there's something that you just want to find f of x, right? So f of x is what you want to find, okay? And f of x is just determined by 4 numbers, actually, in this case. Finding what, so if you want to find an f of x, all you need to specify is for every x what value f of x takes, right? It's a table. For every x value, for every x value, few values, what values you take, f of x, right? So I'm just isolating the problem as, okay, let's fix an x, and I'm asking what value should f of x take here. And the previous discussion was just saying that the value that f of x takes here has nothing to do with values that it takes elsewhere. If you look at the problem, it's just a one-dimensional optimization problem. In a sense, you're just trying to figure out the scalar value, as in a single real number that you want to plug in for f of x that minimizes this expression. So this has nothing to do with x primes, x double. What's happening elsewhere is irrelevant. And it so happens that for this, the optimal, the scalar value that you plug in is this particular constant z, which is equal to expectation of y given x is equal to x. Okay, which I just expanded previously. So this is just one number that you can compute for every x. Okay, and this is what is the best f in terms of EP. Okay. Yeah. They are minimizing the expectation.
Effectively, for the minimum value. So we are selecting the minimum value in y.
No, we are trying to find that f which is closest to y in this expectation sense. You know, so you want, so see, think of it this way, right? I can substitute any value for f of x. Thinking of it as f of x is kind of occludes the picture. Just think of it as I want to put in a scalar, some z. Okay, so I want to figure out some z that minimizes the expectation of y minus z squared. Okay, that's all I want to find.
I just want to know because x equals more x. So does that mean like the big X is in the condition of just one x, or it's the condition of whole x?
No, so the variable has been specified, has been plugged to a value which is
X
little x.
equal 1, so the big X equal 1.
Yeah.
That means we just find that I have the beta for that kind of X.
There is no discussion on beta yet.
Yeah, I mean fx.
So the variable x takes a, when I write little x, the variable x takes a particular value. For example, it can take value 1, 2, 3, 4. You know, in my example, in the previous example, I was just saying x. So the variable x takes a value 1, 2, 3, or 4. Then let me fix one of the values. You know, I'm going to do this for every value, but let me focus on one value. Let's say 1. And for 1, I'm just saying I need to figure out just one scalar, which is f of x. And I'm saying that scalar is just this guy, which are not true here, but we will discuss it later why this is true. But this is the, so for every x, if you can just compute this number, that is the best f in terms of EPE. Yeah. Any question, confusion? Yeah, I thought about why this is optimal. I thought it was obvious. Now I don't remember. So let's see. It's okay. We will revisit and figure out the intuition why that is correct. So given, okay, so the reason why we defined, why we figured out what is the best f is because we want to now think back to the two models that we looked at in the first lecture, which was the k nearest neighbor and the linear model, right? There were two things that we saw in the first lecture. We're going to now kind of understand what exactly they're doing. They are actually approximating this expectation. Okay. So which expectation? This expectation that I'm talking about, this conditional expectation of y given x is equal to x. So let's look at the first guy, which is k nearest neighbor. I'm going to just use k and n as a shorthand here, the notes. So first observation is that if you think of this is an expectation of y given x is equal to x. And what is KNN doing? It's all it's saying is, okay, give me an x, give me a data point x, and I will try to sum over all the xi's, near x, and I will sum the yi's over there, right? If you remember the k nearest neighbor expression, I think it is the k. I'll try to find. Give me a test point. So give me any point. I have some data, which is xi, yi's, which are any number. Give me any data point x, okay, a generic x. Maybe we should call it x0 so that you guys don't get confused. Let's say some new point came along for which I want to figure out its its value, right? Its y0 is what I want to figure out. Okay, I have been given xi, yi, which are any number, I is equal to 1 to n. So I've been given some data points, some realizations of the input variables, output variables. That's the data that I have. Using that, I define this k nearest neighbor model, which all it's saying is, give me any new point, x0, and I will find some k xi values in my data, which are closest to this guy, right, x0. For example, Euclidean distance, you can just compute the distance between 2 points. And then I'm just going to average the values of the y's that I've seen in my data corresponding to these xi's, and I'm just going to, the average involves a division by k, 1 by k, because I'm averaging k numbers. So that's the k nearest neighbor rule, so if you remember from the first class. So you can interpret this in terms of approximating this best f. Okay, so k nearest neighbor is not doing something naive. It's actually trying to approximate the guy that you're supposed to approximate, which is this conditional expectation. Okay, I'm saying it's conditional expectation because there's a vertical bar here and there's something on the right side. It's a conditional expectation. Okay, so why is that? You can see that so first of all, if you had many data points, like let's think of situation one, simple case. Okay, let's say x0 was given and I wanted to find the value of x0 or value of y0 actually. Let's say in my data that I already have, maybe there was some, maybe x1, x2 and x3 were actually the same as x0, but they were exactly the same point as x0. Okay, they're overlapping the same value that I've already seen in my data. Okay, then you can approximate this guy, expectation of y given x is equal to x, as just the average of, let's say it was 3 particular x's in my data set which were the same as x0. Then I can just take the average. So this is approximately equal to 1 by 3 of actually not capital, sorry. Okay, ignore the k there. Y1 plus y2 plus y3. Okay. Let's say x1, x2, x3 were the overlapping ones, then this expectation is actually approximately this guy. In a sense, if you get a lot of these overlapping points, you are essentially getting the value of this expectation of y given x is equal to x. Okay, that is what is the first approximation. Okay. And the second approximation which leads us to this is that let's say they're not overlapping. Okay, I have some x's which are close to the x0 that I want to figure out. I am still averaging. Okay, I'm still averaging, and that's what this expression is: 1 by k sum over xi near x0 of yi. See, that's the connection between the best f. I guess this is called the regression function. Okay, and the k nearest neighbor expression. So that's the first non-trivial. Yeah, now you kind of relax the overlapping issue as well and say, okay, okay, let me draw a picture. So let's say x0, let's say this is a 2D plane. Okay, x0 is somewhere. Let's say you want to find what is y0, right? What is the... I want to find y0. Okay, which means that I have a model which can say what y0 could be, a prediction, right? So let's say in a simple case you had, you have data points xi, yi from your, I is equal to 1 to n. Okay, you have these n data points in your database, or it's a string data, it's called. You can always try to see if there is already some xi which actually is equal to x0. Okay, maybe there are 2 or 3 of them, or maybe there are 10 of them, maybe there is none of them. Okay, if there is some xi's which are actually overlapping with x0, then you can actually approximate the best function as just the average of what you already seen. Okay. The second thing is, let's say they are not overlapping. Now maybe there is an x1 here, x2 here, maybe there is an x5 there, maybe there is an x3 here, maybe there is an x4 here. Okay. So maybe there's nothing in your data set which is actually equal to x0. So how do you make a prediction for x0? KNN, what it's doing is saying, okay, let me look at in a small neighborhood of this guy. Let me see what all points are there. In fact, what are the k nearest points to me, which in this case just happens to be, in this example, x1 and x2. Then I'm going to take the values of x1 and x2, which are at different points now. They're not at x0, right? I know the values of y1 and y2, but y1 and y2 were for x1 and x2, not x0. But I'm going to average those two. So that's the k nearest neighbor rule. So that's the second level of relaxation or approximation. So the first level of approximation is why am I calling it an approximation is because if you knew the joint distribution of x and y, you can compute this expectation. Okay. If you knew probability of x comma y, because I told you expectation is always a summation over distribution times the value, right? If you know the distribution, you can always do the sum. If it's doable, yeah, it's doable. If you know the distribution, you can always compute the expectation. Okay. Expectation is like less information than distribution. Because with a distribution, you can also compute variance, you can compute other arbitrary things. So If you knew the distribution, you could compute this.
On what basis are you deciding the value k?
Yeah, k is not specified. So the decision of how to pick k, we're going to discuss that in a few minutes. Okay. But all I'm trying to connect is that we discussed about KNN and linear models last time without any notion of statistics or anything like that. This time, in today's class, we defined a joint distribution over x and y. We defined a loss function and the expectation of that loss function. Which model minimizes that EPE value, which is a loss, error value, right? That function happens to be, for every x, that function takes a value expectation of y given x is equal to x. Okay, that's how the function is defined. So if x takes 4 values, for every value, just compute this thing in this thing here. Okay, that is the best model that you could compute if you know the joint distribution. But you've been given data set, you have not been given the joint distribution. Okay, so the data set, what do? You work with models like KNN or linear model or something like that. We are saying that, okay, we have been given data and KNN does something reasonable. It's trying to approximate actually what's the best thing you could have done if you knew the joint distribution. Okay, that's the connection. Yeah, it's not clear how to pick k value yet. Yeah, it's not coming up here. Yeah, it's not. Yeah. If they happen to be close by, so actually, yeah, let's say, so this, in the first simple case, I said wherever x0 is, there is actually x0 is equal to x1 is equal to x2 is equal to x3. I just have 3 data points in my data set which exactly are x0. Then whatever value they take, maybe they take the same value, which means that averaging is, this is nothing, it's not doing anything, right? 3 numbers divided by the same, which are same divided by 3 is the same number. K is what? Not yet. You can say k is 3 here, but this is not the k nearest neighbor method, right? If you remember, k nearest neighbor was saying for any given point, find other points which are closest in, k neighbors which are closest, and then average, right? So, yeah, you can say k is equal to 3 here, but this is not k nearest neighbor. Yeah. So that's the connection between statistics and the KNN method. Okay. Okay, so actually let's take a break for 10 minutes and then we'll resume. Yeah.
So I would like to know for the sample, what do you want to have, like, so you want us to cut our codes and just provide you so what else do you want?
Did you have a look at the questions?
Yeah, just like that. So we have the classification,
So you just have to write some code, which you'll see in the last session. Actually, I've given a link to the tutorial, I think the same thing. You just write like a few lines of our code and get a performance number. That's it, you just report the number. So for this computation experiment, all you need to give back is the answer that you use and the numbers that you produce. Output. This is nothing to do with minimization. This is just a definition of it. So we have to minimize the amount of numbers. We're trying to minimize this. For fixed x, this is the only thing which we can change is the f of x. For fixed x, f of x is just a scalar. So the only thing we can change is f of x. This is anything is also an angle whatever. It should be something which minimizes this expression. So actually I think this is without this x. So we fix capital X from value. So that's not changing anything. Condition on x is So G dx is just whatever function it is. Given x just means it's the same thing, right? I just showed you.
Conditional distribution of the
Yeah, I wrote it a couple of times. Yeah, it's a redundancy here because if I write here already, then I don't need to write
just
it.
splitting it up. It actually doesn't do a role, but we are just splitting it up. Summation from here.
Yeah, if you fix an x, the summation goes away. Or you can just find in case g of x is the squared error, then just find the f of x. That's a statistical one.
That's And here, so when it's not close, we use this expression. Just relate it.
When it's not overlapping.
Overlapping, yeah. So next to
It's never going to overlap. I just gave it as a case. Yeah.
This average makes sense because it's like they are the same.
Yeah. So if it overlap, this average is actually the same one. Actually, like if you have lots of overlap, then like for example, instead of number 3, you have number 300. Then it's actually exactly probably very close to this type. It's just something a law of large numbers. Things are going to be the same as the true, unknown true expectation if you have lots of averaging. In the non-overlapping case is what KNN is defined. So all I'm trying to relate to it's not connected, right? So the connection is something I skipped. I didn't skip, but I'm going to talk about right after this, which is that they've shown that KNN as n and k go to infinity and k1 goes to 0 is actually it's not log large numbers. It's almost difficult to get, but it's okay. No, this is not. Yeah, log large numbers is a general set of results.
How does the summation break up? You are doing the summation, right?
Yeah, I wrote sum is this split up. Just it's in the same manner, right? So this is split into two things. This is a function of x, this is just a function of y given x.
This is like this multiplied by this.
Yeah. So I just if you pull it back in, there's a double sum and you have this product of this and this. This is just a joint distribution.
But this and where is this one?
All the values x is take, all the values y take. Right? That is what was the definition of expectation. All the values that all the variables take, somehow all it's a huge summation, right? I think here this is just a definition. I said
X into y combination.
X and y combinations, X into y. If x takes 4 values, y takes 10 values, and it's 4 times 10. Ask if you have any questions about the random variables and stuff.
Very random question. Over here, the y that we're considering, it's not result, right? It's no result. It's x and y are two different events. Just for probability we are considering.
So done a course in statistics. So do you know what an event is?
Yeah, I know.
Okay. So random variables are so there are two words, right? Events and random variables. You should not get confused between them. Okay. Events are sets actually, like die takes value odd numbers, these certain sets.
So x is basically an instance of random variable of event 1 and y is a random variable of event 2.
There's a mapping from random variable to events. So your question is now?
My question is for every instance, for every realization, we have where there's an x, there's a y, and then there's an f of x. That's how
f of x is a function of x. So this is a deterministic function of.
Right, and we're calculating that.
We are just asking for what f of x should be the right one, which minimizes this expression.
So in the end, basically, that's what we're doing. Right? In the end, for every realization, if to calculate f of
but only x has realized, y has not realized. Oh my god, that is something else. How do we clear this? Okay, so x is realized, y has not realized. That's why we still have an expectation of y, given x is equal to x. So x has realized. We're just asking for y has not realized. So let me draw a picture. Nice to have. So, okay, this is just an aside. So think of, let's think of y and x, okay? Then not don't think about regression and all that stuff, just think of it as, let's say it's a Gaussian, Okay, this is just a two-dimensional crossing, and what we're looking at is the top view. So it's actually supposed to be like a bell-shaped thing, like a bell or something like that. Okay. Now, when I say x is realized, all I'm saying is let's say x realizes little x. Then this y has not realized yet, right? So y is still a random variable. In particular, it's actually y is going to look something like this. If you look at the distribution, y is still a random variable. For a fixed x, y is still a random variable.
Basically, so the value of y is not predicted. That is what
The value of y is not fixed yet, so it's still a random variable, and that's why we're taking expectation there.
Okay.
And we're asking what is that value of f of x that is closest to y, and it happens to be the mean function actually.
Can you just repeat the last statement? What is that value of?
What is that fixed? Let's forget about f of x. What is a z which minimizes the expectation over y of y minus z squared? That's what we're asking. Let's ignore x. Once x is realized, you can pretty much delete x from the picture. And I'm just asking what is the z which minimizes this. And
so basically there's an x, there's a y, and then there's an f of x which is z, which is basically finding out the closest value to y.
Yeah.
That's it, right?
Yeah. So once you fix x, all f of x is supposed to be a function of x. So once you fix x, f is supposed to tell me something else, right? Like it's a function. Now, but we have not decided what the function is. That's what we want to decide now. Okay. So that's the only degree of freedom. And I'm just calling, instead of thinking of it as f of x, I deleted x from the picture completely, at least in this here. I'm saying, just think of it as x is fixed. All I'm asking is what value can f of x take, which means what value can z take, which minimizes this expression. And z
But
can only take
that expression,
just
closest value to y.
closest to y closest in terms of this. Yeah. If you substitute that will be the lowest value for this, and any other z that you substitute is gonna give a higher value of this expression there. Right. So let's say z star is the one that's closest in y in this sense. Okay. Then if I substitute y minus z star square, expectation over y is going to be less than any other z. That's what minimization means, right? Y minus z square for any other z. That's what this means.
Going ahead, we can minimize this by either KNN or either Rayleigh square method, right?
No, we have not yet. No, we said we already minimized that, and that's why somebody asked. So the minimization of this is actually this expression. There's nothing to do with any statistical models yet. But this is a function of your John distribution, which you don't know. Okay? Because you've only been given data, not the John distribution. Okay? And because we've been given data, now we are approaching from the method side and saying, are the methods actually actually doing the same thing as what you would do if you knew the John distribution?
Same thing I have to when we talk about approximation, are we not passing the approach?
We will talk about bias and variance soon.
Exactly, that's why I didn't ask it, because we have system bias.
Yeah, it's going to be controlled by the K thing.
Yeah. And one more thing, Professor, there are two books, right? So is it a priority if you follow ESL and ISLR, or because I find myself more comfortable with ISLR?
Yeah, then please continue to read that one. It's fine.
There's nothing like that. Both of them contain the same thing but in a different manner.
No, this is more technical.
This is but I'm going to start.
Which is fine. Yeah, please go ahead.
Catching up with ISLR with better as compared.
Which is good. Yeah, please go ahead with that.
It's absolutely right. Yes, once I get through with the basics probably then I can catch up, but I can connect it here when we're talking.
Sure.
Just doing that.
Yeah.
So just wanted to
Yeah. Okay, so let's actually go into resume. So welcome back, everyone. Not everybody's back, that's okay. So we just saw that the k-nearest neighbor, forget about this stuff here, the k-nearest neighbor is actually trying to for every given x naught, which is maybe a test point which is not in your data set, it's actually trying to give you a number which is close to this guy. Okay, this conditional expectation of y given x is equal to x. Okay, and that's what it means to be a good model, because the model which just only depends on your data that you are already seen, the n data points, is actually trying to come up with an estimate, come up with a prediction of, let's say, y naught, which, if you had lots and lots of data, is actually going to be this number, which is expectation of y given x is equal to x. The number on the left side is actually a function of the joint distribution, which you don't know. The joint distribution object, or whatever it is, you don't have access to it. You only have access to data, which is xi, yi, for I is equal to 1 to n. So given data, you are still able to somehow approximate the right quantity, which is this expectation of y given x is equal to x. Okay. This is actually specific to the loss function that we use, which was the square loss. So we'll see later, if we change the loss function, what happens. Okay. So that's the summary for the first part. Any questions? Is everybody still with me, or some of you are lost? Yeah. It's not difficult, so we just need to work it out. Let's do it after the class. It's not, I'll just post it in the same notes, but let's do it after the class. So I just showed you, okay, KNN gives you approximately the right quantity if you have lots of data. Okay. When I say right quantity, all I'm saying is KNN can do the right prediction, because this is just an approximation of the best predictor that you could have figured out if you knew the joint distribution. Okay, which minimizes the particular least squared loss in expectation, the EPE value. But is this the end of the story? It's not, because even if KNN does really well in approximating the best thing that you could have approximated, KNN suffers from several issues, and that's why there are all these other methods. Otherwise KNN would be the end of the story. If you had small data, okay, if you only have like three coordinates of your input variables, and you have millions of them, then you should probably not do anything else, just do KNN. You should be fine. But the moment you go from 3 coordinates of your input variables to maybe 30 or 300 or 3000, it's not uncommon actually. For example, at Google scale, for click prediction and stuff like that, they have millions of variables. So a million coordinates of your x variable. So that's a really large matrix, a large vector to look at. So for such settings, KNN will definitely not work. So that's what I want to quickly discuss, which is the curve of dimensionality. And I just want to give you an idea of what exactly is this curve of dimensionality. When people build new statistical methods, new statistical models or methods like linear regression or variants of linear regression, or random forests or things like that, we'll see later, all they're trying to address, or at least one of the key issues that are trying to address, is this curve of dimensionality. Okay. So what breaks when you go from your input variable being 3 dimensions to 300 dimensions? Okay. And you can look at it without thinking about prediction models or statistical modeling. Okay. So what is this curve of dimensionality? Let's try to get an idea about it. Actually, skip one thing. Okay, so I'm skipping a couple of pages in the notes and going to curves of dimensionality because it's a tangent, but it's good to have an idea of, because of that's why we're learning all these methods. Okay, roughly. So what is curve of dimensionality? So let's say we have a square. Okay, so our x input variable is just 2-dimensional, and it only takes values in the square. Okay, so maybe it takes values something I think last time we had a two-dimensional data anyway, so something like that. So let's say x takes values there. Then you can ask a question. Let's say I want to look at a 10% volume of this input space. So when I say input space, x is two-dimensional, so x1 takes some values, has a range, and x2 has a value, that takes a bunch of values, so it has a range. So so volume for two dimensions is just like area. So let's say this is 10% of the area. The question is, what is the side length needed for covering 10% of this volume? Okay. So let's say this is a unit square, which just means that this is 0, 1, 1. Let's say it's a unit square. I'm just fixing the vector space here, two-dimensional vector space. So let's say I want to cover 10% volume, in this case 10% area. Let's say this top left corner. Actually 10% is a wrong number. I mean, not the right number. So let's say it's 9%, because I want to have good products. So what is the area of what is the area of a square? Yeah, side square, right? So whatever, some I guess I use the notation L. Okay. Anyway, side square is equal to whatever 10% of this volume, which is just 1, right? Okay, I'm still thinking it's 10%. Okay, so 9 by 100, right? So what is the side length? 0.03, right? No, sorry. Okay. Now, one manifestation of curves of dimensionality is this. If you have I don't know if I can give numbers here. There's actually, okay, let's actually. Can everybody see this diagram? It's a bit light. So this picture is actually just trying to show you what I want to illustrate. So I'm gonna so let's pick p is equal to 2. Okay, p is just the dimensionality of your input variable. So p was 2 in our case, and the unit we're looking at the plane, so p was 2. So for that, I think this is the 10% of the volume. So you can see that is actually giving a side length. So they say distance, but think of it as a side length. That is 0.3 as you guys computed, right? Can you see this point here that I'm showing you? So on the x-axis is the fraction of volume. So I want to cover 10% of the volume of my input space, and I said, okay, so that let's pick the top left corner of the input space in the two-dimensional case, and we just figured out that for that we need a side length of the smaller square to be 0.3, right? Which means that the x-axis, x1 and x2 both have to have a range of 0.3 out of one unit. I want to cover 0.3 to get a 10% volume in that square, right? And the reason is because of multiplying products, right? Even if I have huge ranges, which is 30% of the x-axis and 30% of the y-axis in that 2D plane, still I only get 10% of the volume, right? Okay, because I'm multiplying 0.3 with 0.3 to get, forget 10%, so it's 9%. Actually, in this example, I think we use 10%, so poverty into 10%. But anyway, side lengths multiply as products. That's what gives you the volume in a space. In a 2D space, it's just the area, and in 3D, it's going to be a cube like this, right? For a cube like this, if you multiply 0.3 times 0.3 times 0.3, you will get what? So that is 2% of the volume, right? Or 3% of the volume. Yeah, instead of 9% you went back to 2%, then you kept the same side length, right? So as you increase the dimensionality, the volume that you're covering is reducing actually exponentially, like because of the multiplication of the side lengths, right? So even if you were covering 30% of the range of each axis, in 3 dimensions, like first axis, second axis, third axis, if you're covering like in this picture here, if you're covering 30% here, 30% here, 30% here, this volume out of this unit cube is just 3%, right? As you computed, okay. And you can imagine if you have 10 dimensional cube, which you can't imagine, but if you have 10 dimensional cube, then if you keep the side lengths to be 30%, 30% of the whole range on each side, then the volume is going to be minuscule, like 10 to the power minus 4 or something, I don't know. So that is the cause of dimensionality. So for the same, so this is the inverse plot here. For the same volume, the amount of x, each dimension's range that you need to cover is very high. So for a 10-dimensional cube, you need the side length of your cube to be 80% of the total length. So if you had a unit cube just means in each axis it's 1 unit. So 0 to 1 is the value that that coordinate of the input variable can take. Okay. So you need to have a range which is, let's say, 0 to 0.8. Okay. So it's not very intuitive, right? You're covering so much on each dimension, but the volume you're just capturing is just, in this example, 10%. Okay, in this picture. So the notion of nearest neighbors breaks down because think of points, your data points spread uniformly in that 10-dimensional space. Okay, but to cover 10% of volume, you need to have a cube which is covering the range of each variable, which is like almost the whole range. 80% of the range is like saying I'm covering all the points pretty much. Okay, so that's the issue. So nearest neighbor wants points close to it, but to find the close points in a small volume around the x0 point, for example, you need to, for each dimension, you need to have like a really long range. Okay, that's the issue of dimensionality. So in other words, if you keep the ranges of the neighbors small, then you will not have any points. Like the volume would be almost zero. It's like you will not find any point in near to your query point x0. Okay. Actually, let me use the thing again. Yeah. So that's the issue with nearest neighbor. So although if you have lots of data and low dimensions, probably you can just use nearest neighbor method for some suitable k. We're going to decide what k is later on, would be enough for your job because it is approximating the best function that you could find if you are using the squared error. Okay, if you change the objective to be, instead of y minus f of x squared, you change it to be y minus f of x to the power 4 or something else, then maybe KNN is not approximating that the thing that the right f of x, but it is approximating the right thing for EPE actually. But if you have less data and more dimensions, then all bets are off. KNN doesn't work. Okay, and that's why we are looking at other methods. On the other end of the spectrum is the linear model. So let's look at linear model where it does in the probabilistic interpretation. So what is linear modeling doing? So linear modeling is just is assuming that f of x is just. So linear models are all about assuming that f of x is x transpose beta. Okay. So capital X is not a vector, as I pointed out in the last lecture as well. Capital X just means the input variable. Okay. So linear models want to assume that f of x, I don't want to look for any arbitrary f of x, I want to pick an f of x which will be of this form. So beta is the parameter of this function. Okay. it so happens that if you want to minimize over all betas of that EP expression. What is the EP expression? Expectation over xy, or probability of xy, okay, of y minus f of x is exactly x transpose beta, so let me just write x transpose beta, okay, square, right? This was the EP expression. I just substituted instead of f of capital X, I just substituted the exact form that we're assuming, and so this is what would give you the best linear model. Best linear model if you know the joint distribution. You can only do this minimization if you know if you can expand this out and have all the numbers in the expansion, right? This is, if you remember, I had expanded it out last time. So, but it so happens that you can minimize this as a function of the joint distribution, which is as follows. So let me write that expression first and then we can discuss it. There is the expectation of x transpose inverse expectation of, this is I guess expectation of x, and this is expectation of x and y of x times y. So see, all these are these are input variables and output variable, okay. So so this is the, so if you actually minimize this, you get this, okay. So I'll do the derivation later on, but I'm thinking whether I should do the derivation right here, because it's related to the derivation that we did last. I mean, we didn't do the derivation, but we wrote an expression. Okay, let me write down the expression. So just a few minutes ago, I wrote what is the best f you can get when I'm not assuming anything, like this linear model, and I related it to KNN, right? That KNN is approximating roughly the expectation, which was this guy here, this guy. So this was the best f without any assumption about linearity and all that, and KNN was somehow approximating this expression, right? If you assume linear model, okay, which is like this, then the best function, because beta pretty much parameters this function, the best function is actually this, okay, is the expectation of x transpose. So x transpose, what is its dimensionality? Just as a check, huh? What is it? Yeah, it's a square matrix. It's actually a P cross P matrix. Okay, x is just remember, x is just a input variable, which is p-dimensional, let's say. Okay, so then it's, you can see that x is p cross 1, and then x transpose is 1 cross p. So this x transpose is like a p cross p matrix. It's actually related to the covariance matrix, if you remember, but it's not necessary here. And this is just a vectors, because x is a p cross 1 vector and y is just a scalar. Let's say y is just a 1 cross 1 thing. So and I'm going to just write down what we didn't derive it explicitly, but last time, if you remember, linear modeling and least squares, we had an expression for beta. Did I put a hat there? I'm not sure. Let's say there was a hat there, which was actually x transpose. X is now, these are matrices. X transpose x inverse x transpose y. Okay, this was, if you remember from a previous class or some other class where you saw linear regression in the vector form. So this is a function of data. So xi, yi, which are I is equal to 1 to n in number. Given data, I can compute this. Okay, these are, I stack the x's as rows in my x matrix. Remember what the x matrix was? X was a x matrix was just x1 transpose to xn transpose. So this is a n cross p matrix, right? From the last week's notation. So this is the beta. This is a model that you would get if you minimize least squares, and this is the model that we are saying we would get if we restrict ourselves to linear models, and we are trying to minimize this, not any function of the data. We are minimizing the function of the joint distribution of x and y. Okay. So you will see some issues here, like there's like if you just superficially look at the expressions, there's a transpose somewhere else. There's an x transpose x here and then an x transpose. Don't get confused. The x here is a input variable. The x here is the matrix X. That's why I put a bar on the top right. Okay. It so happens that I don't know if you're going to prove it here, but this first expectation of x transpose inverse, which is a function of your joint distribution, which is a function of just the distribution over x, is approximated by this matrix transpose matrix inverse. Okay. So this expression here is approximating, I don't know, complicated, but this is approximating this guy. Okay, and this expression here is approximating roughly that guy. Okay, so linear modeling that we saw last time without any vocabulary of statistical modeling was actually approximating the right thing. Okay, the right thing would be if you knew the joint distribution and you want to minimize this loss, which is a least squares loss, or the joint distribution, this is the expression you would get. Okay, so that's the connection between k and n, and no assumptions about the function, and assuming that the function is linear and least squares. Okay, that's the analogy between those two methods and statistical modeling. Any questions here? Is the analogy not clear or? So I'm just trying to see 1 second. Okay, so all I'm saying is, see, we had this EPE expression, right? Remember? So there was an f of x here in the general EPE definition because it's a function of f, and we wanted to minimize all f's. Because if you minimize EPE or all f's, that would be the right function because it's minimizing some objective, and so that would be the one which would do prediction such that it's minimizing that objective. We fixed the f of x to be linear model because we are in linear model setting. So I just replaced the x transpose beta here with f of x. Now, without proving anything on the board, I said the best, if you minimize beta of this expression, the best beta, which for every beta you basically get a number, right? So this is you want to get the beta which gives you the lowest number for this expression. This is evaluates to a number for every beta. So the best beta is actually expectation over x of x transpose. Now I just was talking about the dimensionality of x just so that it's clear what x transpose is. It's just a p cross p matrix, and it's actually so expectation of x transpose inverse. So it's inverse of what is called the covariance matrix times the expectation over x and y of x times y. Y, let's assume it's a scalar, so we are doing regression, multilinear regression. So that's the expression. Now I was just trying to relate that to a beta hat that we had seen as a closed form expression last lecture for least squares problem. That closed form expression was x transpose x inverse x transpose y, where x's are matrices. So I should call matrix x transpose matrix x inverse matrix x transpose vector y. Okay, so what is the matrix x? I just wrote it down here. And what is the vector y? Vector y is just y1 to yn. So this is my data. So what I'm saying is least squares was all about data, right? I'm not thinking about any distribution. I'm just given the data, I just compute this p-dimensional vector beta hat, and that's my model. Okay, I'm just going to use the beta hat for every new point. I'll just use beta hat transpose that new point, and that's my prediction, right? On this side, we're not looking at data. Sorry on that. So what happened there? Okay. On this side, we are not looking at the data. So over here, we are not looking at the data. We're just saying, given the joint distribution, what is the best beta? If I could restrict myself to linear model. So I'm just relating these two. I'm saying that least squares is actually approximating the best beta. That's by just inspection. I'm just saying, this matrix x transpose matrix x inverse is actually an approximator of this covariance matrix inverse, and the second term is an approximator of that part. Okay, it's like an approximation of something that you would if you need a joint so the thing is this, right? The whole field of statistical modeling is because you don't know how the data is generated. If you knew exactly what the distributions which generated the data, you can always work with expectations and the joint distribution, and you don't have to do any of data modeling. You only see the data, so that's why your models are typically functions of the data, like beta hat is a function of the data. And here we're just trying to say that if you have lots of data, then this term is going to be pretty much an approximate for this guy, and this term is going to be an approximate for that guy. So just an analogy there. Is that clear? Okay. Okay. So now I introduced the expected squared prediction error for a function. Okay, I was mostly talking about regression task, I guess, because I was talking about y's, and y's, as we know, are quantitative output variables, right? Now, what do I do with qualitative output variables? We never discussed that. In the last lecture, I said if it is qualitative and it happens to be taking two values, cat versus no cat, then I can just map it to be 1 or 0 and just do regression, right? But let's define an EP for the qualitative task explicitly. Okay. So for that, we need to define again L, okay, which is gonna kind of quantify. So instead of f of x, I'm gonna now call, g is gonna be my variable that I wanna predict, right? G can be cat versus no cat, let's say it's just binary. And instead of f, I'm gonna use here, for some reason I'm using g hat of x, okay? In the regression case, I'm using f of x. Here, I'm just using g hat of x, okay? Yeah. And to define this loss, if you remember, g only takes two values. Let's say, for example, g is only takes values 0 and 1. Let's say 1 corresponds to cat is present and cat is absent in a picture or something. Let's say input is a picture which is two-dimensional. So then you can see that this function, this loss function, can actually be specified using 4 numbers, okay? Which is what values does g take and what values does g hat of x take. If g is the same as g hat, maybe there is no loss, as in I am predicting correctly, okay? Maybe I'll put zeros there. And if g happens to be cat and g hat happens to be no cat, maybe I don't like that g hat is producing I don't like that g hat which produces no cat when there is cat. Maybe I'll give a loss value of 2 units, some number. And maybe when there is no let's call it this, I really don't know. But when there is no cat and g hat says it's a cat, I'm fine, because maybe I can infer that. I can do some post processing or something. Or maybe all I'm saying is I can have a different value there. I can have a 1 instead of a 2. Okay. I can have different values for how much do I value my incorrect prediction. Okay. When there is a cat and I say no cat, maybe I value that outcome, more. It's not that bad compared to when there is when there is no cat and I say cat. Okay. But it can be symmetric. In a sense, I can put a 2 here. Doesn't matter. So that's how you specify a loss function. Just like in the regression case, I specify the loss function by saying square of the difference between y and f of x. Right? Now, the EP expression, now it's supposed to be a g hat, I guess. Is similarly split. It's actually expectation of over x, and then there's something inside. Last time I didn't expand it out, but the inside is just going to be summation over. Let's say g takes 2 values, then I don't want to. Yeah. Let's say g takes two values. We're looking at the example, right? So then what is the loss of g taking a value 0 and whatever g hat produces times probability that g takes a value 0 given x is equal to x, okay, plus loss of g taking a value 1 and whatever g hat takes, g hat says, okay, times probability that g is equal to 1 given x is equal to x. If you remember the EP decomposition that I did, if you remember the John distribution can always be split as probability over x times the probability of y given x, right? So that's what I've done. So x, let's say x is a picture. Then picture, I don't want to, pictures, how many different pictures can be there? There are too many. I don't want to expand that, so I just wrote it as expectation of x. And outcomes from is just 2. So either g takes a g, the reality is that g is 0 or the reality is that g is 1 because that's a random variable there. And g is equal to 0 with probability this given x is something, and g is equal to 1 with probability this given x is the same thing. Okay. And there is, this is just the expansion of what is that expectation there. Okay. The conditional expectation of loss given x is equal to x. For this, again the same trick that you don't have to, so you can look at it as for every given x can I minimize this, okay, to find the g hat. So for every given realization of x is equal to x, we can tell what is g hat of x, okay, for a little x. And that just happens to be, we can actually prove this, but we're not going to do it in the class. So it's a max, or here, I guess not max, in this example, it's just going to be, I guess it's a max over p of g is equal to 1 given x is equal to x, or p of g is equal to 0 given x is equal to x. Okay. All it's saying is the right model that you are supposed to pick is, if given that x, okay, given that picture, if there is more likelihood that it is cat compared to not cat, then you should predict cat. And that's the intuitive thing, right? I mean, given the picture, if g is a random variable here, so g can take 0 or 1 with some probabilities, two numbers, right? G is just a two-dimensional random variable. So those are the two numbers, probability of g is equal to 1 or probability of g is equal to 0. Okay? So which one is higher? Okay? Let's say probability of g is equal to cat is 0.6, probability of g is not cat is 0.4. Then you should predict the best predictor which minimizes that particular loss that I wrote here. The loss, I didn't write, let's call this, I can replace 1 or 2 here. Let's say I pick symmetric loss, so I take 2 here. Then the best predictor is actually the highest of the two probabilities. Okay, if the probability, the real probability that the picture, given the picture, it's a cat, is 0.6 and it's 0.4, it's not a cat, then you should predict at which point it's a cat. Okay, that's very intuitive, right? I'm not saying anything complicated here. I'm just saying there are two possible probabilities given the picture of cat, given a picture, either it's a cat or not a cat. If it's a cat with 0.6 and if it's not a cat with 0.4, predict it's a cat because 0.6 is higher than 0.4. Okay, that's what this maths operation is doing here. But that's if you knew these conditional distributions. Of course, we don't know these. Given a picture, what is the probability that it's a cat and what is the probability it's not a cat, right? That is where we're gonna we can actually again see that this is again related to, or actually approximated by k nearest neighbor. Okay. So k nearest neighbor in the classification setting, what does it do? It doesn't do the averaging that you see in a regression. It's gonna look at the neighborhood of some, let's say I've been given a new picture, x0, okay? Let's say x0 in the center. I have some x1 here, some x2 here, some xk here, which are the k nearest guys to this point, this new point. And it will say, okay, what is this picture about? Maybe it was cat. What is this picture about? Maybe it was not cat. What is this picture about? Maybe it was cat. Okay. So just find out of your in your k nearest neighbors, how many were cats and how many were non-cats, and whichever proportion is higher. Okay. Just predict that as the prediction. Okay. If you had, let's say k is 10 and you had 6 cats and 4 non-cats, then just predict that this for new point, for this point for which you have looked at the 10 points, it's a cat. Okay. So that's what k nearest neighbor for classification would do. Okay. I mean, it's the same as averaging. If you remember last time I did something weird, which was that I said indicator of that number, some average 1 by k y is greater than 0.5 or something. Right? If you think of cats being 1 and non-cats being 0, then if there are 6 cats and 4 non-cats, then it's, sum of y is 6, k is 10, so it's 0.6 is greater than 0.5, right? And so I will classify it as a cat. It's the same thing, I mean, if you remember from the previous class. Okay. So what I'm saying is, k nearest neighbor is still approximating the best thing that you could do if you knew the joint distribution, whereas k nearest neighbor is operating on just training data. Okay. And so this classifier actually, if you knew the true data as the joint distribution between x and y, this classifier, which is the max over p of g is equal to 1 given x is equal to x and p of g is equal to 0 given x is equal to x, is called the Bayes classifier. Let me just write it here. It's called the it's just so if somebody says Bayes classifier, then this is what they're talking about, and it's something that you don't know because it's not defined over data, it's defined over the joint distribution of your data, which you don't know. Okay. And there's a nice picture. Where is it? Yeah. So this is for the same 2D data that we saw last time. This is the Bayes classifier. It's going all over the place, but this is the best classifier for the given the joint distribution of this data. So they somehow knew they generated the data, so they knew the joint distribution. Given the joint distribution, at every point they figured out whether it's cat or not cat, in this case orange or blue, and they connected those dots, and that's why it's that's decision boundary is this, where they are exactly not sure whether it's cat or not cat. Right? That's the decision boundary, if you remember. So it's unwieldy actually. So this is a right thing that you're supposed to predict. But a linear model will just put a line there, and KNN in a different case would put, because it's data based, it would be either smooth or it will be all over the place, a jagged thing, right? So that's the connection there. Let's go back. Okay. Okay, so I want to kind of wrap up the statistical decision theory, or just this language of using joint distributions to somehow talk about the losses with respect to distributions, and then talk about how methods are approximating them. I want to just wrap it up by one last thing, which is this generalization of this loss. So EP was talking about squared loss, right? But why squared loss? I can put arbitrary functions there which talk about take y and take f of x and then spit out a score, right? I can do other things, and so one key generalization generalization is what is called the method of maximum likelihood estimation. It's in section 3, beyond expected prediction error. Okay. So that is the maximum likelihood estimation problem. Let me not think about statistical modeling for a second. I mean, in a sense, not think about classification and regression. Just think about let's say you observe data. In this case, I'm gonna not think about my regression classification problem. So let my data be just z1 to zn, which are just realizations from a distribution p theta. Okay. So think of it this way. So I have an example, right? So I said initially at the beginning of the class there was this normal distribution with some, let's say, mean 0 and variance 1. Okay. So I would have a, let's say, a random variable which is distributed according to is a standard normal basically. So it's mean 0 and variance 1, which means that this basically just looks like this. Doesn't go to 0 actually. And the probability that z takes a value, let's say minus 0.5, is this vertical bar there. So that's what that's the notation that that's the example that we saw at the beginning of the class. So I'm saying, let's say z1 to zn maybe are drawn from the standard normal. Let's say here I've just put p of theta. Why did I put a subscript theta? Because I want to say, for example, in general this can be. In general, this can be, oh my god. Okay. So anyway, let me rewrite this. So in general, it can be nu and sigma square, right? So these would be the parameters. So think of theta as being maybe a vector with a two-dimensional vector, because there's a one-dimensional distribution parameterized by two numbers. So let me just call it, maybe theta is this. Okay. So that's why I'm just general notation here is p subscript theta. Now, the maximum likelihood estimation method is going to estimate, the goal is going to estimate theta. I guess it means right. Estimate theta, okay. And how do you estimate theta? You will have to use your data, right? And just like a database method, it's going to use z1 and zn to estimate theta. And the way we're going to do it is first define a loss function, which is L of theta, very similar in style to EP of f, okay, which is going to be equal to sum over I is equal to 1 to n, the log of the probability or theta of z is equal to zi. Okay. So what is the probability that z took the value zi? Take the log of that. I mean, log is kind of inconsequential in a sense. Log is just being used to have some summation. But anyway, it's beside the point. They've just defined the loss function of any given parameter as this. Okay. This is called the likelihood function. Okay, L of theta is called the likelihood function, and this is, so we're talking about generally. Let's say we have observed n data points from some distribution. Think of it this way, right? It could have been xi comma yi observed from the joint distribution p of x cross y, right? It could be that as well, but for us, all I'm saying is, given n data points from any distribution, as far as I know, like some parametric distribution, maybe it's from normals, all I want to figure out is what is the mean and the variance of the normal, then I want to maximize the likelihood function. Okay, this is the likelihood function, this sum over n of log of p theta of z is equal to zi, and the negative log of that you can minimize. So whenever you maximize the function, you can minimize the negative of the function without any issues. Okay. Why did I bring this up? Because we're going to look at the EP for the linear modeling problem as an instance of likelihood maximization problem. Okay. So let me make that connection. So what was the okay, not the EP problem, but let's think of the least squares problem. So let's remember the least squares objective. It was the residual sum of squares. Okay, RSS of, let me use theta now instead of beta that we use, the model as the sum over I is equal to 1 to n of yi minus actually I don't even have to use linear modeling or any okay, let me use linear model, it doesn't matter. Xi transpose beta square. Remember, this was the objective of the linear regression, the least squares problem that we saw, right? Actually, I mean, whether I use theta or beta, it doesn't matter. Maybe in the notes I've used theta, so let me continue with the notation theta. So I'm gonna just relate this to our likelihood maximization problem. Okay, so that gives you
Is that log base 10 or the natural log?
It's actually inconsequential, but just assume base 10. Actually no. Actually, let's assume natural log. So base e. Base e. Do you know what is the natural log?
Yeah, log base of e, which is 2.7.
Yes. So we're going to use that. In fact, let me substitute that explicitly. So I'm going to define what that log is. So let's assume. Okay. So I'm going to do something with the joint distribution such that I'll actually get this RSS eventually. I mean, such that figuring out the maximum likelihood estimate is the same as minimizing the RSS objective, which is this residual sum of squares. So let me assume that y is actually equal to x transpose theta plus some errors. Okay. So I'm going to assume that the output variable is actually related to the input variable through this transformation. Plus some error, and I'm going to assume that x is not random, okay, and I'm going to assume that this is, let's say, 0,1 for simplicity. Okay. Remember, in fact, if you want me to expand it out, y is, let's say, 1 cross 1, which means it's a scalar or just a one number. X is p cross 1. X transpose is 1 cross p, sorry. X is p-dimensional, and theta is also p-dimensional, and is 1-dimensional, and y is 1-dimensional. Okay. Now if I assume this, then the probability of y takes a value little y given x takes a value little x is actually just let me put 3 equal to here. I'm not going to expand on the n, so it's just going to be x transpose theta comma 1. Okay. Why is that? Because see, the only y is a function of input variable x plus some this epsilon here. And epsilon is the only thing which I'm saying is random. X is not random. So for every given x, y is just a shifted normal distribution. It's just a shift with a constant because x is not random. So let's assume x is fixed to be some number, some vector. For every fixed x, this is what this means. So for every fixed x, y is just a normally distributed random variable with certain mean and some variance. Okay. Now, since it's parameterized by theta, I'm going to put a theta here, okay? Because if you see this, the x is, as I said, is not random; it's data. I'm going to substitute data there. Theta is the only thing that is going to determine how this normal distribution looks like, right? What are the centers of this? What are the means of this normal distribution? So if I do L of theta, okay. For this guy, there is sum over I is equal to 1 to n, and there is a log of probability of theta, right? So let me write the log of what is probability of theta that y takes a value y and x takes a value x. Okay, so that's going to be 1 by square root 2 pi times 1 e to the power minus y minus x transpose theta, because that's the mean. X transpose theta is the mean. Sorry, let me just use brackets here. Square divided by 2 times 1. Sigma I just took to be, the variance I took to be 1, as you see in the model. So this is the expression for, happy to be the expression for the Gaussian. Okay, so if you have not seen this before, just assume that this is a rule. This is just by definition. Okay. Okay, so and if you see, let's focus on this. Let's focus on the log of this thing. It's just going to be, let's focus on that. It's going to be equal to log of 1 by square root 2 pi. And log and the exponent cancel, right? Log is to the base e, and that is e to the power of something. So that's minus y minus x transpose theta square divided by 2. Okay. So log of this entire thing inside the bracket is just this. Any confusion here? Yeah. Which step? This from here to here? Oh yeah, it's just a, sorry, it's not the loss of theta, it's a likelihood function. I just defined it. Yeah. So that's just the sum over log of p theta of whatever is inside, right? So if you remember, since I'm assuming epsilons are random variables, and random variables with 0 mean and unit variance, y's are random variables with 0 mean and unit variance given x. Okay, so I'm gonna substitute this guy in that L of theta you saw earlier. So L of theta was defined for some p theta of z. Here the z is going to be y is equal to y given x is equal to x. Okay. So that p theta expression is what this is, this whole thing. It's just p theta of y is equal to y given x is equal to x is just normally distributed with this mean and variance 1. If it's a variance 1 distribution and y is a one-dimensional Gaussian, then it's 1 by square root 2 pi e to the power minus y minus x, y minus the mean, which is x transpose theta square, divided by 2 times the variance. Variance is again 1. So this is the expression. I took the log of it, and that's where I got log of 1 by square root 2 pi times something. Okay. Sorry, minus something. Okay. And okay, what you may be wondering is, where is this I? Where did I miss the I? So it's actually supposed to be, yi and theta I. Okay, because we only have data. So this is yi and theta I. And so if you look at this expression, this you can ignore because it's a constant. It's log of 1 by square root 2 pi is some constant, some number, but I don't know what it is. So L of theta. So I'm going to use the notation proportional to, by this symbol. Okay, just means that I'm ignoring that initial first term. It's proportional to minus sum over I is equal to 1 to n of yi minus xi transpose theta square. There's a divided by 2, but I can kind of ignore that again in proportionality because it's a constant. Okay. So maximizing the log likelihood, actually, the likelihood function. Okay. Did I say it was a likelihood function? It's a log likelihood function, sorry. Without the log, it's a likelihood function. Okay. So maximizing the log likelihood function is the same as is proportional to minimizing residual sum of squares theta. You see the expression for residual sum of squares, that's what this is, right? So that when we are doing residual sum of squares, we did not talk about Gaussians or anything like that. We said, okay, we have some data, some realizations of input and output variables. We're just gonna say least squares objective as the, so that my linear model is close to yi's in my training data, and that's how we got the objective for residual sum of squares in the first lecture. But what I'm saying here is that if you assume some model for the joint distribution So in fact there is no joint distribution because I assume x to be non-random, so you don't have the distribution on x. Okay, so x is like a fixed quantity that is irrelevant to this. So the only distribution that you are concerned here, if x is fixed, is the distribution on y. Okay, and we said if the errors or the epsilons are normal, then y is just a shifted normal. Okay, shifted with this new mean. Shifted with this new mean, and since I assume this normal assumption on the distribution of y, I can maximize the parameters of this distribution over my data. That's what I'm doing here by maximizing the log likelihood function, and that just happens to be the parameters of this distribution of y given x happens to be the parameters for the linear model, and so that's the relation between maximizing likelihood and residual sum of squares. The bottom line or the key takeaway from this part is that the choice of least squares objective corresponds to some Gaussian assumptions on the data. Okay, so minimizing this is somehow implicitly saying that you probably made an assumption like y was Gaussian. Okay, I mean it's not a strong formal statement. I'm just saying that minimizing this is equivalent to thinking that y was Gaussian and maximizing likelihood. But what if you chose y to be some other distribution, right? Do you guys know any other distributions other than Gaussian? Let's say, discrete or continuous distribution, anything, uniform, discrete distributions, multinomial distributions. So there are arbitrary distributions, right? So many, some exponential distribution, things like that. So you can assume other things, and then you'll have different objectives, and they will not correspond to least squares objective. Okay. So that's the link. So the maximum likelihood method kind of encompasses the least squares problem as a special case. Okay. So, and it also gives you a principal way of defining the objective function. So in least squares I said y minus xi transpose theta squared. Okay. But why not cube here? Why not 4 to the power 4 here? Okay. So those are considerations that you can principally choose if you think in terms of the maximum likelihood estimation problem. Okay.
Professor, we started with the assumption that the error function is non-distributed.
Yeah.
That's why we came to this conclusion.
Yes. So that's what I'm saying. It's equivalent. If you assume errors are normal, then you would optimize the same objective as the residual sum of squares. Okay. But you may think that it's a restrictive assumption, but if you're minimizing the residual sum of squares, and go to your manager, the manager will say you are making a normal assumption. Because if you make a normal assumption and try to maximize likelihood, it's the same as saying you are minimizing the residual sum of squares. So it's the same objective function, the same optimization problem, and same theta will be obtained. Okay. But the nice thing, so you may say, okay, I'm assuming assumptions about my errors and so on, maybe it's too restrictive, but making those assumptions will let you do more, as we will see maybe potentially next class. Making these assumptions will let us talk about confidence intervals for theta or beta for the linear model and so on. Without making an assumption about this joint distribution or the conditional distribution in this case, you can't talk about confidence intervals. Okay, you might have seen confidence intervals in some previous class, so we're gonna revisit that and talk about why you can talk about confidence intervals. You can only do that because you're making some assumptions, and we'll see what they are. We have another 10 minutes, so let's see what we can do. Is there a lot of confusion, or some of these hazy but somewhat okay? I mean, it's acceptable, right? We are not glossing over, just accepting everything as a fact. I mean, a couple of derivations I did not do, but everything else came from a very principled look at what is the objective, what is the distribution, what are the functions that we care about, and how are they related to empirical methods like KNN and d-squares. Okay. Let's pick up one more thing. So So before we actually so let me actually now derive, it's easy to derive, so in the next 5-10 minutes, let me just quickly derive how we got that expression. So I did take I said beta hat is, like expectation of, or not hat, let's see, let's get this. I said it's expectation of x transpose inverse expectation of xy, right? Or I said in the other case, I said beta hat is, x matrix x transpose matrix x inverse matrix x transpose vector y. Okay, so I just said these are true, and I said it's not easy to prove. And I think we used this guy in the first class. Did not use, but I did bring it up in the first class, and in this class I brought this up. So we can probably derive one of these because it's not difficult. Because least square subjective is something which is nice. It's just a periodic function actually, because there's a square there, and we are assuming linear models. So we will actually derive this. Okay, so I'm just saying, okay, so let's do it for the second one, because otherwise we'll have to manipulate expectations all over the place. So what is what is beta hat? Beta is actually, if you minimize over betas, all betas of your residual sum of squares, or beta, you will get beta hat. Okay, not equal to okay, let me not even introduce the notation. So if you minimize this is the right guy, this is the beta hat that you're supposed to get. Okay, so what is the residual sum of squares? Let me just write it in matrix form. It was okay, let me write it in first in the non-matrix form. It was sum over I is equal to 1 to n of yi minus xi transpose beta square, right? This is fine. Okay, now I think in the last class I said, okay, this is I can equivalently express this in a matrix form, and for that I had defined the X matrix as the matrix of x1 transpose to xn transpose, n cross p matrix, right? And beta was p-dimensional, and bias was scalars. And so I also introduced this other matrix, which was the not matrix but vector, which is y1 to yn, right? This is n cross 1. This is fine from previous class, right? So residual sum of squares is actually just the same as y minus x matrix times beta transpose y minus x matrix times beta, and we'll just check this by examination. Why is this true? So remember, this is actually an n cross 1 matrix, n cross 1 vector. Actually now it's a 1 cross n because of the transpose operation. Because of the transpose operation it's 1 cross n, and this is n cross 1. So inner product of two vectors of same dimension is going to be a scalar. So that's, at least the dimensionality is fine. It's a scalar or a single number. Now this is actually, well, if you really expand it out, so I'm going to actually do it in a very gory detail. Let's say, so the first row of this matrix is this vector is going to be yi minus x1 transpose, y1 x1 transpose beta. Okay, actually if you want to check that, if you remember, x beta is x1 transpose to x, actually I've written the other, xn transpose times beta. So each of these is p-dimensional, and this is p-dimensional. This will give me a vector which is n times 1 dimensional, where an entry is going to be xi transpose beta. Sorry. Is that fine? So all I'm saying is X matrix times beta is an n cross 1 dimensional vector. The way you can see that is because X matrix is just every row is a vector which is your realization of your input variable, right? That's why operator transfers, because convention is all vectors are column vectors, so that's why I transpose them. And beta is a column vector, it's the right thing. So if you multiply these two, x times beta, you can see that the first entry of your vector would be x1 transpose beta, because there's nothing, it's a row times column. If you remember the multiplication rule, you multiply a row with the column element wise. In this case, there is really no row and column, because there's only one entry in the row and column has one entry. So the x times beta vector is n cross 1 with xi transpose beta as the entry, ith entry. Okay, that's why you get a x1 transpose beta at the first entry, and similarly the ith entry would be yi minus xi transpose beta. Similarly elsewhere. So, and you can see the first term is just a transpose of that. This is just transposed. Like that. The first vector, which is 1 cross n, is just a transpose of the n cross 1 vector. Okay. And again, if you use the product rule, how do you multiply, find a product? It's element wise, right? So if you look at the ith entry, it's only getting multiplied with the ith entry, and it's the same scalar value, so it's a square, and you sum the squares, that's what you get the RSS objective. Okay. So I guess what I'm saying is this is the vector notation for RSS objective. Okay. So now let's quickly look at the so y minus x beta. Actually, I did this derivation for some student after the last class, but I'll read it. Y minus x beta is equal to y transpose y minus x. Okay, I'm just expanding the product here. So y transpose y, okay, and then y transpose x beta. Okay, first term of this guy, and now the second terms. Minus beta transpose x transpose y. Okay. Why is that? Because AB transpose, you guys know this rule? Okay, it's just B transpose times A transpose. And then the last term is going to be plus beta transpose x transpose x beta. Right? Now if you take the first derivative, so what do you want to do? You want to take the derivative with respect to beta. But the thing is, beta is a vector. Okay. But we can still proceed. Okay, first term is anyway, the derivative is 0. So first term we don't care. The next two terms, they are functions of beta, right? So actually, let me simplify this. This term is y transpose x beta, right? And this term, actually all these terms are supposed to be scalars, because RSS is a scalar value, right? So each term has to be a scalar. So I can take the transpose of this term, actually, this term, and that would give me y transpose x beta. The transpose of the scalar value is the scalar value itself. So it gives the same thing. So minus and minus. So anyway, there's a minus 2 times y transpose x matrix times beta. So that's the second term. So let's say this is term. The first term anyway 0 if I take the derivative with respect to beta, because it doesn't involve beta, it's just beta. So get rid of that. And the third term and the last term is going to be beta transpose x beta. Let's keep it. It's called term 2. Okay. And and I'll at least do term 1. So term 1 is just like, it seems to me the first term is just something like A transpose beta, okay, where some A. So A here is going to be this transpose of this multiplier, okay. See, beta is P cross 1. Whatever multiplies with beta has to be 1 minus P because the whole thing is supposed to be a scalar, right? So I'm going to just do the derivative of this. This is actually just sum or I is equal to 1 to P of AI beta I for some A, for any A actually, A vector, okay. Then the derivative of, let me pick a beta J, okay. It's a scalar. So what is the derivative of A transpose beta with respect to the scalar is just AJ. Like in the sum, only one of them is beta j and its coefficient is AJ. So that's the only thing which will remain if I take the derivative of this summation with respect to beta j, right? So if you actually stack the derivatives with respect to all, you can stack the derivative with respect to all j's and you will get AJ and so on, which means the derivative is actually just, the vector derivative is just the vector A, okay, which is P cross 1 dimensional, okay. So at least we know how to take the derivative of these two guys, right, these two guys. The only thing which remains is beta transpose x transpose x times beta. That's a little bit complicated. And because we are running out of time, I'll have to just assume that it is equal to 2x transpose x beta, okay. I will expand this out in the notes and then post the notes, so it should be fine. So let's assume that is correct. Then you will see that, okay, I'm giving a space for that. Then you will see that the first derivative, setting the first derivative equal to 0 will give you the optimum typically, right? So you'll get minus 2x transpose y times, that was the A part, okay, plus 2x transpose x beta is equal to 0, right? Yeah. Okay, that's the A, if you remember, and this is the derivative of second term. And if you do now the matrix manipulation, only this term involves beta, okay. So you can just keep the second term as it is. So 2x transpose, actually delete the 2 because both sides have 2. X transpose x beta is equal to x transpose y, and then you pre-multiply both sides with x transpose x inverse x transpose x. Beta is equal to x transpose x inverse x transpose y, and this part is identity matrix, okay, and matrix times its inverse is identity, so you just get that beta is equal to this thing, okay. So that proves, I mean not proves, but at least shows that that expression is fine. Modulo, I didn't do the derivative for the second term, I'll just do it after the class and post it. So that's it for today, okay, thank you. We'll have these notes.
However, can this be used in practical application, like how it's going to be helpful?
No, in practical application you just blindly apply KNN, then you're going to fail, potentially. Then what are you going to do? Lose the job? No, this is not immediately practical, but this gives you an indication of why things work, why things don't work, and stuff.
I mean, if we take one real-time example, how we can relate these things into a data set.
What do you mean these things, right? And there's some things we discussed today.
Like all these equations, these transforms, like are we going to practically apply the data set?
So when you call a ln function in R, it is actually computing this. I mean, if it's computing something else, maybe you should check why it's computing something else.
If we want to do the performance tuning of a particular LM function, so are these concepts are going to help?
No. Why do you trust that ln function is doing what it's doing? You understand? Like, somebody gave an ln function, but it may be doing something else, right? That means you're coming up with some numbers which you don't know why they are those numbers. Okay. So do you want your business solution to be dependent on a third party, black box? So there is no immediate benefit of this. This is just formalism for building new models and verifying existing models. That's just actual modeling, right? I mean, otherwise you could just do just software. That's an immediate benefit.
I mean, if you want to build a neural how these are going to like.
Yeah, so you may have some special assumptions about the joint distribution and stuff like that. We will see through, we just introduced the notion of statistics and probability today. But throughout we'll use that notion, say we have additional information, then we'll see how new methods get generated.
Do you have lab session today?
Yeah, we have it at night. Yeah.
1 to 2?
It's a 1 to 2 years. Yeah. If not here, then you should go to the PA sessions, right? There are 4 hours on Thursdays and Fridays. They can repeat the same pattern if you want. They're just going to introduce basics of R. So if you already know R, at least today, they're going to just in lab sessions they're just going to repeat the same lecture notes. There's no new material. Yeah, they have the flexibility of repeating notes or doing R depending on the class.
And what are these other ones?
Those are office hours. You can always go, it's the same instructors, right? So you can just go and you can just ask them to repeat what they taught in the class. It's just a 1 hour class, so it should be fine. Yeah.
And we can do them with like our issues and stuff like that.
Yeah. 4 hours, I think you should be able to balance between lab sessions and the Thursday office hours, Friday office hours, and my, office hours.
When is your lab session?
It's today at 1 to 2.
It's today 1 to 2.
Yeah. Same thing, yeah. So today I think he's going to go basics of R. So if you already know, you may not want to, attend it, but today's probably just going to be basics of R and some parts of lecture 1. Lecture 1 is just notation, right? So if you're comfortable with it, don't have to worry. So lab sessions are just optional, so I don't think that you have to attend lab sessions to do well in this course. Fine with the TA office hours and my office hours and the lectures and assignments. Slack you don't have, so can you send me an email actually?
Yeah,
so I will, because I need the email to invite, right? Yeah, otherwise I cannot.
For the course, like, we'll be dealing just with the stats, or we'll be dealing with modeling as well. Like,
This is, you've seen the syllabus, right? So we are looking at regression right now. I think the next class or sometime next class or next 2 classes will finish, not finish, but consider classification. But these are very basic, as in not basic, but foundational things. Beyond that is where you will see the impact of things that you may use in practice, like random forest, cart, or decision trees, and things that you see in the other classes. With this foundation, you'll be able to quickly, easily, understand the pros and cons. Like you'll see the models there, not in the first 2-3 classes. In the second class, you've not seen too many models. You've only seen just linear modeling and analytical.
my question was like, will we be doing this like modeling, like, because when we are using R, you're basically just using the package, right?
You can use package or you can call it up. It's your choice.
Again.
No, you can call the same thing. This is not complicated, right? These are just multiplications.
When there is a package, I guess.
No, then So the thing is, you're trusting the package, right? So yeah, I mean, it's fine in a academic environment, student environment, you're learning. But in a company, let's say you are the CEO of a company, of $1 million company, and you can't just rely on black boxes. Yeah. Maybe you have NDAs and stuff like that, contracts and stuff. But what I'm saying is, this course is for you to. There are two things. One thing is, given the probabilistic language and the statistical modeling language, you can define your own model, which may not fit any of these random formulas, because all these existing models make certain assumptions, which your data will not probably have, and then you are leaving money on the table because you are using a mismatched modeling tool for your data. So that's the goal is to minimize the gap in the sense you should be able to, for example, do maximum likelihood estimation. You don't have to stick with least squares. You can do other things. The moment you know additional stuff about your data. So that's the first goal. The second goal is we are understanding when models fail and when models don't fail. So I said KNN fails because of dimensionality. That is one of the key, I guess, ideas in this lecture. So you should not only use KNN when you have high dimensions. That's like one of the, I guess, thumb rules that you can take with you.
Also, KNN is it not a very computationally expensive
It's not computationally expensive. KNN has to find out neighbors, right? So if you have a data set of size n, there's an order n search. In the sense, every point you need to compare whether it's a neighbor or not and sort it. So maybe you wouldn't have order n log n time. But it's linear in the number of data points. Maybe it's bad because if the number of data points is million, then you spend a million units of time.
Define k as well, like the optimal k of
K you'll have to figure out using cross validation or something like that. We'll get to that again. We'll see all those issues. So yeah, so the second goal I was saying was just pros and cons of existing models that you already know. So you may use LM function in R, but it has its own shortcomings. So you'll see these are just ways to think about these models and packages. Yeah.
Professor, for the project, what kind of project do you require? Is it supposed to be real in the
No, it's up to you. You can do whatever you want.
Okay, so
In the sense of, I mean, just follow the instructions and just recommendations in the project page. You can always talk to the TA and me if you have some specific thoughts that you want to work on. Don't be too ambitious. It's fine to, according to your background, if you want to have an applied thing where you're doing exploratory analysis of a specific data set in your industry of choice, then it's fine. This is for you to kind of, because nobody's going to give you CAN problem typically in the industry. So this is just a component to kind of make you pick a problem and actually do, something.
I mean, that is the first lecture. So for midterm and final, is it going to be kind of a big assignment where we have to apply packages?
No. Midterm and finals are going to be pretty easy because it's going to be easy and it's probably just going to be some class notes at worst.
and we'll get the dates for the finals soon, right?
Finals week, I don't know when they're going to be announced, but I hope there is a fixed finals week. I will let you know earlier.
I know.
Yeah, within that.
Because one of our subjects is ending on 9.
Okay.
So it depends when this ends, so just book a flight and for the vacation back in India.
I don't know when so I'll check out if they have already announced. They probably have not announced as far as because it's basically classroom scheduling for finals week. I don't know if that happens this early, but I can check and get back to you. And send me an email about this flight.
Yeah, sure. Thank you. Thanks.
Professor, having assignments do we need to form groups? Is it individual?
The submissions are individual, So you have no obligation to form a group with anybody, but you can do study groups to discuss, things that you answer. Individual people have to write down their own solutions and submit. So, but if you collaborate, you need to report who you collaborated with, especially if the answers are.
So we can do it and we can let you know that.
No, because point is just, the groups are just for you to kind of understand the material really well, and then maybe some hints for the answers, but not, can't discuss the exact answers. but there's this honor code. So if you discuss hints for the assignments, then you should probably report the, because we don't know. So if we see two answers and two codes which are exactly the same, then we will err on the side of caution, right? So you want to report things. But it's fine to discuss on forms and groups. Yeah. We're going to discuss, so I skipped one section here, so we're going to discuss that the beginning of next class.
And regarding the last, we have a session today.
We have a session today at between 1 to 2, right here.
What exactly is happening?
They're going to introduce, I think he told me that he's going to introduce, he's going to discuss basics of R. I have given them the TAs full freedom to do what they want, but I guess no, because
any material that they'll be using in
so I need to check with them. So I don't know how they're going to conduct. They have full freedom, and as far as I know, I've only told them that no outside content has to be discussed. It has to be within the everything from the lecture notes only at most. So they're only going to discuss at most lecture notes, repeat some parts, or discuss issues with the modeling part.
When that's the question, so the equations and everything, the derivations that are in the talk, how much of this will come in the exams? As in, we have to kind of be very thorough with the derivations or something, or it's just majorly R that we should be practicing for this course. So R is being harnessed through assignments. So in the lectures you'll probably not see much of use of R. But since the exams are at most going to be based on lecture notes only, so you need to be thorough with the lecture notes. You don't have to. I mean, whatever. So if I derive something, then if I don't derive something, not. You should at least know what's going from step A to step B or something like that.
So
We'll see. I mean, we'll calibrate it, and we are not here to make things hard. So, or neither do we want to make it easy because we want to learn something. So, we'll calibrate it.
I'll be taking from in November because I'll be going back to India. Our sister is studying part time.
Okay.
From 17 to there's a class on 18.
Okay,
There's some submission.